Thank you very much. So thank you very much, Rak, for organizing this meeting and for giving me the opportunity to present this work. So I will be talking about comments on quivers and fractons, and it is based on a short paper I put on the archive last summer. So it is a talk where I will try to not to answer any particular question, but I will try to connect different subjects. So one of the subjects is the subject of quivers, which is well studied in our community, and it appears everywhere, and it is one of the main heroes of this workshop. Okay, so as I said, I will speak about comments on quivers and fractons, and I will try to combine two subjects, one of which everybody knows very well, and another is the subject of fractons, which became fashionable recently. So my goal will be to phrase the theories of quivers and the associated physics in some kind of a fractonic language. We'll see that there is a direct analogy between the two. So the talk will be about drawing some analogies and asking some questions rather than answering questions. So the outline of the talk will be as follows. I will review what are the theories of lattices, both as condensed matter theories, view of them, and I will formulate or slightly like reformulate the language we use for quiver theories in the language of lattices. Then we'll consider these more weird lattices that people are studying recently, these fractonic lattices, and we will discuss how the quiver theories are actually very, very analogous to these fractonic lattices if one views them in a certain way. And finally, we will make some comments about all this story and geometry and how these notions can be understood in a larger framework of higher dimensional geometries and field theory. So let me start from what are the lattices. So the lattice theories are kind of ubiquitous theoretical setups or devices that people use all over physics, in condensed matter and statistical physics and so on. So typically what we have some quantum mechanical model where we have vertices and edges and plaquettes, let's say in 2 dimensions, and then there are higher dimensional analogs. And then we put some degrees of freedoms on these special points, say either on vertices or edges or plaquettes, and we turn on Hamiltonian, which couples these degrees of freedoms. So this is some kind of quantum mechanical model, which is very, very simple. We study it thoroughly when we are undergrads and so on. But these systems exhibit a lot of interesting physical phenomena, and they describe real phenomena in nature, and as well, they are very useful toy models. Okay? So there are actually 2 ways to think about these lattice models. So first way is written here. These are just quantum mechanical models. You can think about them as one-dimensional quantum field theories, where the degrees of freedom just happen to be labeled by points, edges, or plaquettes, and so on of some lattice. Okay, so this lattice, you can think about it as some completely abstract creature. And the only thing you are doing, you are studying some quantum mechanics. Okay, this is not, however, usually how you think about these models. Usually, you think about them in this second picture, where you think about the lattice as really being a lattice in some real space, and you have just some degrees of freedom being localized at some points or edges and so on. For example, there is some atomic lattice that is effectively described by this effective spin Hamiltonian. Okay, so again, you have one dimension which is continuous, which is the time, and you have d dimensions. In the case of the previous slide, the d being 2-dimensional lattice, it is some discretization of real space. Okay, so given this picture, there is of course an obvious generalization. So we can consider a lattice, but instead of putting a quantum mechanical model at each, say, vertex or edge or plaquette of the lattice, we can put there quantum field theory. Okay, we can put, instead of spins, we can put fields, which depend now on some continuous dimension. Okay, so before we had dependence on time only, now we can have dependence on space and on time. Okay, so we put a d+1 dimensional quantum field theory on a d prime dimensional lattice. Okay, and again we can turn on some interactions which are now conveniently described by some action principle. And this action couples degrees of freedom living on different points of this lattice. So again, one way of thinking about this lattice theory is as simply as the d+1 dimensional quantum field theory, where fields are labeled by some abstract lattice. So this I can stand for the vertices or edges and so on. Or there is another way, which we'll discuss, is that as if we have a theory which lives actually in d plus d prime special dimensions plus a time direction where d dimensions are continuous and d prime dimensions are discretized. Okay, and this is a funny picture to consider, although it was considered before, and we will discuss it during the talk. So, so this is the picture you can have. Now, this is not a completely abstract game that I'm playing here. Of course, we have a lot of examples of such quantum field theories, which with a lattice associated to them, and we call these theories Quiver theories, right? So here is an example of a 4D Quiver theory, which will be our main example today. So again, we have a two-dimensional lattice. Okay. So, so we'll have Quiver theories, and now we have this lattice, and we have gauge groups. In this case, it will be SUN gauge groups living on the vertices of this quiver, and in particular, we'll have some gauge fields and some other degrees of freedom, such as gauge genus and so on, associated to the vertices, since these theories will be supersymmetric. And we will also have fields which are associated to edges in this quiver. These are these bifundamental matter fields. And in this particular quiver, we have three different types of lines: these vertical lines, horizontal lines, and diagonal lines, which and the associated fields, I will call them A, B, and C. So we have different types of interactions. We have, of course, gauge interactions, which we can think of as being associated to the vertices, and the superpotential interactions which are associated to the plaquettes. Okay, so there are many such theories. This will be our main example, but you can build theories with other gauge groups and other types of lattices. For example, there is a geometric picture that we will revisit, in which these types of quiver theories arise, say, from string theory and from setups which are related to string theory. In particular, the quiver theory, which is drawn here, can be thought of as a theory corresponding to a torus, to some hexagonal lattice on the torus, which is a very old story. It's a particular example of a tiling of a torus, and there are many other examples that one can consider. Okay, and these largest classes of n=1 theories labeled by lattices are again a classic subject in high energy physics. In some senses, lattice models are classic subject in condensed matter theory. So you can study a lot of interesting phenomena of strong coupling dynamics, such as duality, emergence of symmetry, and so on, in the framework of these lattice models. So as with the lattice models, we can have two interpretations, which I already mentioned. So one interpretation is the way these theories are usually defined, is in terms of some quantum field theories in d+1 dimensions, such that they have fields which happen to be labeled by some abstract lattice. Okay, like the lattice models in condensed matter can be thought of as quantum mechanical models with fields labeled by some lattice. On the other hand, and this is the point of view I will mainly take today, we can also think of it as a d plus d prime plus one dimensional theory, such that the d dimensions are continuous dimensions, d prime is the dimension of the lattice, is a discretized dimension, and then we have a time dimension. And this also is a very old idea going under the name of deconstruction. And we will see how this, we will try to add basically one item to this general ideas of the construction in what follows, and that item will be related to something called fractonic lattices that we will mention. So one question that one should ask is, does the picture 2 really make sense? So if we want to interpret this lattice as some physical lattice in some real space, we need to ask whether there is any notion of locality on this lattice, okay? So in the condensed matter lattices, the spin lattices, we have nearest neighbor interaction or next to nearest neighbor interaction or so on. So there is some notion, since it is really a lattice, an atomic lattice that we can engineer, there is some notion of locality on the lattice. But here in general, if we write a generic quantum field theory, which is labeled by a lattice, it will undergo a renormalization group flow, and then couplings will become strong, and there will all notion of locality on the lattice will be lost. Okay, so as solution to this problem, a way to construct a local lattice, in a sense, is to consider theories which are conformal, okay, which don't undergo a renormalization group flow. And then there is a notion of weak coupling. We can define some parameters in the theory and take these parameters to be small. And then, as we will see, you will be able to define a notion of locality. Of course, we know a lot of examples of conformal field theories, and the Quiver theory I have drawn before is a special example of a generic class of theories. Maybe many people know the degenerate cases of this quiver. So n equals 4 is a special case. The n equal 2 necklace quiver, which is also very well studied, is another special case of this quiver theory. So we have this toric quiver with L1 gauge nodes along one cycle of the torus and L2 along the other. And these are just 2 degeneration limits of these theories. So it's well known that this theory is conformal. And it is also well known that this theory is conformal. And it is a very old result that this theory is also conformal, but maybe not everybody did these computations by themselves.
Shlomo, can I ask a question? Why is conformality has to do with locality?
I will explain in a moment in a bit more detail, but the point is that we want to have some notion of locality in the sense like that the interactions between objects we build from fields on one side of the lattice and with the objects we build on very far locus of the lattice, that these 2 objects don't speak to each other or speak to each other weakly. Okay, so as long as we move along the lattice, like the mixing between objects is suppressed. Yes.
So, but there can be, you can probably dualize a theory that somehow
yes, I will discuss it.
like
so
long-range interaction.
Okay, so to keep your question, I will yes, I will go there. We'll discuss this soon, but that's where I'm going. Okay, so let me just make very simple comments how you compute the dimension of the conformal manifold and how you determine whether your theory is conformal or not. So I just want to say that this computation is very algorithmic. You basically take your conformal field theory, your quantum field theory in 4 dimensions. You list all the marginal couplings. You compute certain Keller quotient, and the result of this computation gives you whether you have exactly marginal deformations and how many exactly marginal deformations you have. So in this case, you would get for general n, you will get 3 exactly marginal deformations. And here, the number of exactly marginal deformations will scale linearly with L1 and L2, and so on. And so the point again that I just made to Jamon's question is that if the theory is conformal, say if we have an operator built from fields at some lattice point, let's call it I, and another operator which built from fields at some distant lattice point, let's call it I plus L, if we can take this coupling to be small, then we would expect that, to connect these operators by interactions, we'll have roughly L interactions that we will need to turn on, and then this mixing will be suppressed by some power of lambda, which will scale as L. So this is a notion of locality that we want to discuss. And now the comment that Jaewon made about the duality. Okay, So why it is important that the theory is not only conformal, but it also is weakly coupled. Okay, and here the duality comes into the game. So in this particular theory, it is also well known that we can take a coupling to be small, but all the couplings to be small, and then we have this notion of locality in the sense of previous slide. But we can also tune the couplings to be large. Okay, we can tune them to be order 1, and we can tune them to be very, very large. And then the statement is that, say you have a weakly coupled lattice where you have these two columns in these two colors drawn here, then you start tuning the coupling to be large, and then in the very large coupling, the theory behaves as if the theory is weakly coupled, but with the order of these two columns exchanged. Okay, so in this very strong coupling, you again regain locality, but the locality is different from the one you started. You kind of mixed up the position of the different lattice points. Okay, and of course you can do it in other ways. You have a lot of couplings here, so you can exchange the rows in the same way by playing with other types of couplings. You can exchange the diagonals by playing with yet another combination of couplings. And if you play most general duality games, you can exchange any lattice point with anyone. Okay? And we'll come back to that in the end. So the role of duality here is changing the lattice. So the lambdas are some kind of a parameters which, when they are small, they give you a notion of locality. When you go to parameters which are order 1, all notion of locality is lost. When you go to strong coupling, you can regain a notion of locality, but it is different than the one which you had in the beginning. Does this answer your question, Jamie?
Yes, thank you.
Okay. So these were general words about lattices and quivers, and basically phrasing of the very well-known facts about quivers in this language of lattices. Now, let us go to the second part of the talk, where we will say some comments about weird lattices, or something I would call weird lattices. So what are these weird lattices? So the usual expectations from these lattice models in condensed matter and in condensed matter physics and in high energy physics, when you just discretize your quantum field theory, is that you have some UV system with some degrees of freedom, and then you go to the IR, you coarse grain this theory, and then what happens is that, you know, fine details of the UV description are typically expected to be lost. Okay, that the theories fall into some universality classes, and the fine details of what you did in the UV is being lost. Now, in recent years, there appear these very interesting models which collectively go under the name of fractonic lattices. Now, these models are just vanilla lattice theories. They are usual lattice theories. Nothing is special about them. If you just look at them, okay, if you just are shown a picture of these lattice theories, they are just very similar to the lattice theory I drawn before. You have some lattice, you have some spins, you have some interactions, so they look completely standard. But when you look in more detail, they have some weird properties. For example, these theories might have something which is called subsystem symmetry. Okay, what that means is that there are symmetries in these models which you can associate to special loci of these theories. Okay, of the lattice points. For example, you have symmetries associated to the vertices or to some lines or to some planes and so on. And this leads to a lot of interesting behaviors, such as having partially movable or immovable excitations on the lattices. Okay, another thing that happens in these theories is that you can have what is called UV-IR mixing. And again, one way this comes about is that fine details of the lattice, which you would think as UV properties of the theory, would affect IR properties of the theory, such as determining how many ground states or what is the dimension of the how many ground states you would have in this theory and so on. What are the symmetries and so on. And so these properties might depend very drastically on the fine structure of your lattice model. And of course, in our community, in the high energy physics community, these theories were widely studied in recent years by Nati, Shueng, and collaborators. And of course, there is a huge literature in condensed matter community also. So mainly the questions that are being asked is what happens in the continuum limit of these models in our community. So the question I want to ask is, what about quiver theories? What type of lattices are quiver theories? Are they usual vanilla types of lattices, or are they these fractonic lattices? And the answer we will get is that, well, they are actually both. They have features of usual lattices and they have features of fractonic lattices. So the way we will address this question, we will first discuss the conformal case, the lattice that the quiver theory, the standard quiver theory that I have written before. And then we will explore the moduli space of vacua of this very simple theory. And we will see that on different branches of vacua, we either get something which looks like a vanilla usual lattice theory, or something which has some properties or features of what we would call fractonic lattices. So any questions till now? Okay. So let us then go back to our quiver theory, our conformal quiver theory, and look at it a little bit in more detail. So one thing that you immediately notice when you learn about these subsystem symmetries, that this very simple quiver theory has something that you would call a subsystem symmetry. Okay. So this quiver theory has a lot of U1 global symmetries. So in general, you have these bifundamental fields. So each one can be rotated by its own U1. Many of these U1 symmetries are broken by the interactions, are either by anomalies coming from gauge interactions or by superpotential terms. And then you can find what are the symmetries which are preserved by all the interactions. And you have this number of symmetries, and the number is roughly L1 plus L2 plus GCD of L1 and L2 modulo some order 1 number of symmetries. And the way to think about these symmetries is that you can associate them to lines running through this quiver. So, for example, you have this line, and what it means that the fields which are charged under the symmetry, which I called alpha here, are the field which this line crosses. So these are these fields here in this column. And the charge, the sign of the charge is determined by the orientation of the crossing of the line defining this symmetry and the lines of the quiver, the lines of the bifundamental lines. So we have three types of symmetries. We have these alpha symmetries, gamma symmetries, and beta symmetries. And since these symmetries are associated to lines on the quiver, the fields which are charged under them are localized on this quiver. They are not, you don't have fields charged under these symmetries which sit anywhere on the quiver, but only on special loci of this quiver. So that's exactly what we define as being a subsystem symmetry. Okay, so the conformal quiver theories have a subsystem symmetry. What are the excitations in this more lattice language that we can have here in these quiver theories? Okay, so let us think about excitations as gauge invariant operators that we can have in these quiver theories. So a natural set of local operators on the quiver here are the baryonic operators, which are associated to the edges of the quiver. So we can build baryons from each one of these edges. And these baryons are very nice local operators. We also have nice non-local operators, which we can build by considering winding the quivers along various cycles. Okay. Now, what we can ask is what are the mobility properties of this excitation? Basically, how the two-point functions of these baryonic operators behave. And since the baryon operators at different points on the quiver are charged under different symmetries, okay, they are charged under, say, a baryon built from this field is charged under the line, under the U1 which crosses it, this line, and the diagonal line coming through this way. And in general, there will be only one such operator which is charged under these given symmetries. the 2-point functions of these baryonic operators will be 0 unless you are sitting at the same exact point on this Quiver theory. So in that sense, you can think of these baryonic operators of being immobile on the quiver. The 2-point functions are 0 if you try to compute the 2-point functions on different loci. On the other hand, if you take two baryonic operators, two different baryonic operators, you can move them together. And maybe the best way to view that is to look at the picture. So if you take a B baryon and the C baryon, they are charged under different symmetries. So the C is charged under this blue symmetry and B is charged under this green symmetry. And they also are charged under the symmetry associated to this column, which I denote by pink color here, but they are charged oppositely. So this combination of B and C is not charged under the pink symmetry. But there are other pairs of operators which are charged under the same symmetry. So you can think of these pairs of operators as being movable on the lattice. So this is again some analogous properties that some analogy you can draw with the theory of fractons. Another thing that we can study is the space of vacua, the moduli space of this theory. And there are two very interesting branches of vacua that we can have here. One branch we will call the Higgs branch, and this is the branch on which we give vacuum expectation values to the baryonic operators. Okay, this branch is very large. The number of baryonic operators scales as the number of lattice points, as L1 times L2. The dynamics on a general locus of this Higgs branch is non-trivial. If you give these expectation values, you will get some strongly coupled conformal field theory. Since these baryonic operators are charged under these symmetries, which we call subsystem symmetries, on generic locus of this Higgs branch or baryonic branch, all the subsystem symmetries will be broken. On the other hand, we have something which we'll call generalized Coulomb branch. And this is the branch where we give vacuum expectation values to operators which wind the quiver. So we have these operators which can wind on the horizontal axis, on the vertical axis, or on the diagonal axis. And these operators actually are not charged under the subsystem symmetry. Since they involve fields which run throughout the quiver, they are not charged on the, under this subsystem symmetry. So if we give them these vacuum expectation values, some system symmetries are not broken. The number of such vacua is related to the number of symmetries, and it scales actually linearly with the scale, with the size of this quiver, and it also scales in some sense not irregularly with the sizes, because we have this GCD contribution. It's basically if the GCD, well, the question is, whether these lines that I draw here, they close on themselves, or they can wind multiple times until they close around this torus. That's where this subtlety comes from. Now, this is about this conformal field theory. And now we would want to consider taking a continuum limit. Now, these theories are conformal field theories. They don't have a scale. So we want to take a continuum limit. That means that we want to interpret this quiver as living in some real space. We want to take the spacing of this real space to be very small, of this lattice in this real space to be very small, given a fixed size of the system, and take the limit of the spacing being 0. But we don't have a scale here. So we need to introduce a scale in order to take this continuum limit. So to do that, we can introduce a scale by going on one of these branches, on the Higgs branch or on the Coulomb branch. So the first thing we will do, we will go on the Higgs branch. And that's exactly the story of the construction. Okay? In the construction, what we do, we start from this quiver theory. We give generic Higgs branch vacuum expectation values, which break all the subsystem symmetry, and we take some scaling limit, and we obtain some strongly interacting quantum field theory, which now lives in 6 dimensions. Okay, the 4 dimensions of the original theory we started with, and if you wish, 2 additional dimensions of the lattice. Okay, so this is the idea. Again, it's an old idea that you have this Quiver theory. You go on the Higgs branch, you take some scaling limit, and you obtain a completely vanilla, well, very complicated, but believed to be vanilla quantum field theory in 6 dimensions, either a CFT or what is called the little string theory, depending on how exactly you take the limit. Okay. And now the question is, what happens when you go on a generalized Coulomb branch of this system? So here, the dynamics in general will be a billion, and thus it will be free. So on the face of it, it looks a bit boring, but it is exactly analogous to going to fractonic phases of these fractonic quivers that we have discussed. These expectation values on the Coulomb branch don't break the subsystem symmetries. So whatever effective theory you can build, in this case, in the infrared, if you can build an infrared effective field theory in 6 dimensions in this case, it will have to manifest these subsystem symmetries since they are there. So that would be the physics in this case. And of course, in the n=2 case, these Coulomb branches were widely studied in the past, and they are still being widely studied. Here we have an n=1 Coulomb branch, and the question is whether we can get any interesting physics, any non-trivial, non-free interesting physics on these branches in some scaling limit. So this is one of the questions I would want to ask. Okay, so this is the main analogy statement that I want to make in this language. So the Quivers QFTs on the Higgs branches are analogous to usual lattice models, and this is basically the claim, the old claim of the construction. But if we consider this Quivers QFT on Coulomb branches, the physics is very analogous to what people are discussing in fractonic models. Okay, so in a sense, this, the fractonic models in the context of Quiver theories, these supersymmetric quantum field theories, is the study of Coulomb branches in these particular theories. We have subsystem symmetries. The number of vacuum scales linearly with the scale of the system. Excitations have limited mobility, and the number of vacuum also scales in some cases irregularly with the size of linear size of the system, like this GCD factor that we have seen before. So now let me connect this story to the story of geometry, to the more modern way of thinking about these Quiver theories. So again, this deconstruction story is a very old story, but between now and when the deconstruction was phrased, we understood something about these Quiver theories, some additional facts about these Quiver theories. In particular, there is a way to obtain these Quiver theories by starting from 6 dimensions. Okay, so what one can do is start from some 6-dimensional 1,0 SCFT. One can put that 6D SCFT on a torus, okay, on a compact space, which is a torus, and introduce defects on the torus, and then go to low energy. And then in low energy, one effectively gets a 4-dimensional quantum field theory, which lives on the lattice, exactly the lattice that we have discussed. So in a sense, it is very analogous to construction of lattice models in condensed matter, where you have some continuous quantum field theory in the UV. You consider a very particular setup, say, of atoms on the lattice, and then you can describe it effectively as a theory which has these spin interactions. Okay, and so these defects, you can think of them as being some kind of atoms in this construction. And again, what I mentioned before, that these exactly marginal couplings, when you tune them, you can change the locality of the locality properties of the lattice. In this picture, changing those numbers, exactly what we are doing, we are moving these defects on the torus. So the position of these defects on the torus is related to this exactly marginal couplings. So the modern view of the confinement, if you wish, is that you start from this theory of atoms, of defects on the torus in some 6D theory, and you deform the theory by removing these defects, these atoms. You give vacuum expectation values, which effectively, their effect is of getting rid of these deformations, and then you get back the continuous theory in 6 dimensions. And depending how you do that, you might get a different 6D theory. Now, the question is, the interesting question is, what is the analogous geometric picture for these fractonic types of lattices or fractonic types of constructions? Or as we saw, the Coulomb branches. So in the Coulomb branches, we start from the same theory. We have a torus with these atoms, with these defects, but now we turn on a different type of deformation. Those deformations are associated to cycles around these Quiver theories. And the question is whether there is an interesting or nice description directly in 6 dimensions of this procedure. An answer of this to this question, I don't know. And this is, again, one of the questions I want to pose. One thing that needs to happen is that these subsystem symmetries that we have, which are basically associated to the, or some of them at least are associated to these atoms, to these defects that we have placed, should be present also in whatever theory we get here. So let me finish just with commenting that, you know, this picture, although we started from a torus and weakly coupled gauge theories, once we understand this geometric picture, we can try to generalize. For example, for theories living on higher genus Riemann surfaces, some of these also can be thought about as some gauge theories with weakly coupled regimes and subsystem symmetries and so on. So the story can be generalized in various ways by understanding this geometric setup. So let me finish with the outlook. So we have made a very simple-minded observation that these novel fractonic phases of matter have a very direct analog in the realm of Quiver gauge theories. And of course, the main question is, okay, what is this observation good for? Okay, so one question is there something to be learned about supersymmetric quantum field theory dynamics by looking about these generalized Coulomb branches? Okay, so one can take this analogy to fractons as a motivation to study these Coulomb branches, these n=1 Coulomb branches, which were not studied enough in the past. And of course, another question, the opposite type of a question, is there something to be learned about condensed matter fractonic lattices by looking at these a priori more complicated quantum field theoretic constructions? But on the other hand, these are very supersymmetric constructions, and we have a lot of control about them. And we have string theory constructions of them and so on. So is there something to be learned? Okay. And then again, the main question is it, you know, it's a question usually asked about these fractonic models. Once you go to this infrared limit, is the theory free, a weird free theory, or is there anything interacting and interesting that we can say? And in this particular case, is there anything interesting fractonic in 6 dimensions that we can say? And all the discussions we had was very special to 4 dimensions and having a 2-dimensional lattice. And of course, a very interesting question is whether this understanding, so general analogy, can be extended to other dimensions, and maybe more interesting things can be understood there. Thank you very much for your attention.